Okay, so this lesson, hopefully you did the warm-up. The warm-up was just a frappy. Remember, we talked about this already, that this line relates to the intercept. This line relates to the slope. The coefficient column is your actual intercept and slope. So there's your intercept. There's the slope. Define the variables if you're using any variables. Then down here, do your estimates of the slope and the intercept parameters have meaningful interpretations in the context of this question? If so, provide me interpretations of this context. If not, explain why not. Yes, they're both meaningful in this one. So the slope for every additional 1 mile per hour increase in speed, the predicted, remember that word, predicted pulse goes up by 16.2809. Y-intercept, when John is at rest, his predicted pulse rate is 63.457, which is reasonable. And then down here, it says here that we just want to find the margin of error, so we only want the part that's after the plus or minus. So remember, the margin of error is the test statistic times the standard error of the slope. If we're doing a 98%, we have 98% in the middle, so there's 0.01 over here and then 0.01 in this tail, which means I have 0.99 to the left there. The degrees of freedom, there were 7 observations here in this particular one. You can it says it right here in the problem. You could also count the number of dots there. So then here in this one down here, so I'm just going to use n minus 2 gives me the 5 there. So 7 minus 2 gives me the 5. There's my critical value. That SEB comes straight from right here, from the chart. And that SE coefficient, remember that row right there is the slope. Multiply those numbers, that's your margin of error. Okay? All right, this lesson right here. So we're just continuing. We did confidence intervals yesterday. So now we just want to do the significance test. So you would either, we're going to stick with HO being beta is equal to 0, which means basically no relationship. And then the opposite would be like that there's a positive relationship, that there is a negative relationship, or there is a relationship. Just like before, you're going to want to write out what beta is, okay? Plan, so identify the appropriate inference method. So in the plan step, the method that we're going to use here is a t-test for slope. Check the conditions. So we have linear, independent, normal, equal variance, and random. If the conditions are met, perform calculations for your work. So then your test statistic, the way your test statistic works is it is the sample slope minus the parameter. Now in this case, we pretty much are using 0 divided by the standard error of the slope. So you can pretty much just think of it as being the sample slope over the standard error of the slope. And the degrees of freedom are going to be n minus 2. Find the p-value, you'd use that CCDF, lower bound, upper bound, the degrees of freedom, again, n minus 2. If your p-value, if your HA is greater than, then your p-value is in the right tail. If your HA is less than, then your p-value is in the left tail. If it's not equal to, it's in both tails, okay? And then that last fourth step there looks pretty much like it's always looked. So if you're given a level, compare your p-value to alpha. If you're not given a level, pick one in step 1. Again, that default is usually 0.05. State if you're going to reject or fail to reject, and then write your final piece in reference to HA. You either have enough evidence to conclude or there's not enough evidence to conclude. All right, so we're going to look at this one example, and we're going to actually solve this one example several different ways. So it says, do customers who stay longer at buffets give larger tips? So Charlotte, an AP Stat student, she worked at an Asian buffet. She decided to investigate this question for her second semester project. While she was doing her job as a hostess, she obtained a random sample of receipts, which included the length of time in minutes, and the party was at the restaurant, and the amount of tip in dollars. Do these data provide convincing evidence that customers who stay longer give larger tips? Here's the data. So first thing right here, the scatter plot, you should be able to kind of answer this question right there already. If I look at the scatter plot, I would be able to say that there is a weak positive linear relationship between time and tip. Again, if this was the AP test, I would write it all out in context. Below, it asks you what is the equation. So it gives you the computer output here. It gives you the residual plot. This right here, when it says residual against the z-score, that is the normal probability plot of the residuals. So there's your normal probability plot. So it says, you know, and this is the scatter plot up above. To create your equation, remember that's your intercept, that's your slope. Define any variables. I'm just defining it as predicted tip there. To do the interpretation, again, we've been doing this already. You just did it in the warm-up, so this is not really anything new. So for every additional minute, 0.03013 is added to the predicted tip. The y-intercept doesn't make sense. If one stayed 0 minutes, the predicted tip earn would be that. Again, that doesn't make any sense. All right, so carry out an appropriate test to answer Charlotte's question. So here, what we want to do is Charlotte's question. She wanted to know if is there evidence that customers who stay longer give larger tips? So she's looking for a positive relationship there. So she wants to know, so her HO is that beta is equal to 0. Her HA is that beta is greater than 0. And beta, again, this is another Greek letter. So beta is the true slope of the regression of tip on time. So remember, you're always regressing your y variable on your x variable. The method I'm using here is a t-test for slope. So the conditions I want to check is this liner. So if you look back to the original graphs, they gave us all the graphs. So there's my scatter plot, and I have a residual plot. If I look at the scatter plot, the scatter plot is mostly linear. The I is the independent. She took a random sample. She took a random sample of 12 receipts, I believe it is. So we have to assume that there's at least 120 receipts. The N, we're going to look at our normal probability plot. That's the graph that they gave me. You could look at a histogram, but they didn't give me that. So there's the normal probability plot. So the normal probability plot is linear. E is our equal variance. So we're going to look at the residuals. Maybe slightly wider here, but I mean, we're only talking about, this is dollars, so it's not like it's a huge amount. So I'm going to say the scatter of the residuals is pretty consistent. And then it was a random sample. All right, so for this next part, I'm going to show you actually 3 ways that you could do the step 3 here. So if you remember, in this particular chapter, I told you that we could still cross off all these things, so we're not going to use these things. So this right here, that one that's labeled T, that is your test statistic. Remember I said in yesterday's lesson that that is not T star. So that is the test statistic. So you can, right here, make your life really easy and say T is equal to 1.23. The number right next to it, that P column, that is the p-value. The problem with this is that the default is that it is two-sided. So unless the problem says that it's not two-sided, you should always assume that it is the two-sided one. I do not want the two-sided p-value here. I only wanted one-sided. So to find the p-value, I would take that 2.247 divided by 2, and I would get 0.1235, okay? So that's one way you could do that. So it's pretty straightforward. The other way you have to do it, so maybe this stuff is also blanked out for you, so you can't see that stuff. So remember on the first page, I told you that the test statistic essentially ends up being the sample slope divided by the SCB. So what I can do then, right here, is I can take that sample slope divided by that SCB there, those two numbers right there. When I do that, I get that. Again, let's say that p-value column is not there, so we want the p-value in this tail. The degrees of freedom, remember they're n minus 2, so in this case it's 10. So I would use TCDF, I'd use that 1.23, positive infinity, comma the degrees of freedom. So then on my calculator, second vars, TCDF, so I have 1.23, E99, and then 10. I hit paste, and again, there's that 1.234 that we had before. Lastly, the last way you could do this one is if you notice here, there's a bunch of data there. So you could type all that data into your calculator, which is what I did here already. So if you want to do that, go ahead and pause your video and do that. And then what we can do is what I have written on the first page is we can use this, if you have raw data, you can use that FLINREG t-test. So what I could do here, I can go to stat, over to tests, and I can go down to LINREG t-test. L1 is where my x's are, L2 is where my y's are. Frequency just stays blank. My HA is greater than regression equation. You can fill in if you want. You can also leave it blank. There's my test statistic. There's my p-value. Go ahead and give me the degrees of freedom and give me your intercept and your slope, just in case you typed in something wrong. Okay? All right, so those are the 3 ways. Do you like that? I just used one problem and did it 3 different ways instead of giving you 3 separate problems. So those are the 3 ways that you could actually solve these things. Okay, so I write that last step the same way I've always written it. This one, it gave me a level of significance, so I'm going to use that here. So the p-value is greater than alpha. So fail to reject HO. There is not enough evidence to say, so you could say to say the true slope of the regression of tip on time is positive. If you don't like that, you could do, there's not enough evidence to say that as time increases, the tip increases. So if you wanted to say that instead, because that was kind of what her original question was, Charlotte, then you could write it like that as well if you would prefer. And then that last page right there, just reminding you of the connection between significance tests and confidence intervals. Go ahead and read the problem. Pause the video, think about it. When you're ready, unpause the video, and I will give you the big reveal. So this one we would reject HO. There is enough evidence to say there is a relationship between the number of miles driven and price. Again, I'm rejecting HO because 0 is not in the interval. Yes, I understand that the interval is negative, Erin, so it looks like the relationship is negative. However, this is what I was testing, so that's why I'm just saying that there is a relationship. That's why I'm not saying there is a negative relationship. I'm just answering the question that HA answered, or HA was asking, I guess. Alrighty, that is it for this one.